Okay, so this is our fourth video on partial fraction decomposition, and on this one I would like to give you an example where the denominator of the fraction has what's called an irreducible quadratic factor. So let's just make one up here. Okay, so here I have the denominator completely factored. This x plus 1 is what we call the distinct linear factor. X squared plus 1, as it turns out, is what we call irreducible quadratic. That means it cannot be factored any further. This is equivalent to saying that no matter what I plug in for x, I can't get 0. If there were a number, if I could plug in 2 for x and get 0, I would know, for example, that x minus 2 was a factor. Doesn't matter what you plug in for x and x squared plus 1, you're not going to get 0. So that cannot be broken down any further. But this is a rational function. The degree of the numerator is 1. The degree of the denominator is actually going to be 3. Degree 2 times degree 1 is degree 3. So we do have the degree of the top smaller than the degree of the bottom. We don't need to use long division first. We just need to know how to split this up as a sum of more than one fraction. One with denominator x plus 1. Another with denominator x squared plus 1, which is what partial fractions are all about. So let's go ahead and see what type of initial guess we're going to need for how this thing decomposes. How do we handle the irreducible quadratic factor? Well, the distinct linear one, just as before, we have a constant over the distinct linear factor. Now, for the irreducible quadratic factor, we know that the numerator should have degree less than 2. So the worst case scenario is for it to be a degree 1 polynomial, and a general degree 1 polynomial looks like a number times x plus some other number. We just don't know what those numbers are. So this turns into find a, b, and c. We'll know how to integrate this, and I will go over how to integrate that when we get to it. Now fortunately, the next step is the same every time, regardless of how the denominator factors. We're going to multiply both sides by this x plus 1 times x squared plus 1 to clear out all our fractions. On the left-hand side, we get x. On the right-hand side, this x plus 1 will cancel. The x squared plus 1 will not. I'll get this. Over here, the x squared plus 1 will cancel. The x plus 1 will not. And now we look for some convenient choices for x, namely choices for x, which make one of these factors 0 to give us a simpler equation to solve for our unknowns a, b, and c. And one of the problems with the irreducible quadratic factor is there's nothing I can plug in for x squared plus 1 to make this go away. It doesn't have any roots, and that's what makes this case a little different. But x equal negative 1 is still a good choice. It will make all this go away, and I should get one of the letters for free here. So I'm going to start with x equal negative 1. I'll get negative 1 on the left. Negative 1 squared plus 1, that's going to be 2 times a plus nothing. So we get that a is negative a half. Now there are no more convenient choices to make stuff drop out. So we're just going to have to pick some nice values for x, which will lead to easy computations. I like x equals 0. So let's use that. On the left-hand side, we get 0. Here we're going to get 1 times a, but a was negative a half, so I've got minus a half there. Plugging in x equals 0 here gives me c times 1. C times 1 is c plus c. So it looks like c is a half. So now to get b, I'm going to pick another value for x, plug it in, use my known values for a and c to get one equation with one unknown, which I'll be able to solve. So the next most convenient choice for x is 1. Let's plug that in. Get 1 on the left. Get 2a here, but a was negative a half, so that's going to be negative 1. Over here, I get b plus c times 2. So let me be careful here. b plus c, c is a half, times 2. So I have one unknown, b. So this we should be able to solve. So let me add this negative 1 over here, get a 2 there. Multiply through by the 2, you get 2b plus 1. Subtract 1 from both sides, you get 1 equals 2b. And we got b equals a half. So now I have a, b, and c. I can write down this with the a, b, and c in, and our original integral becomes the integral of a over x plus 1. That was negative a half over x plus 1. Now the bx plus c, and here's how I'm going to end up integrating that. I'm going to turn that into 2 fractions. It's bx over x squared plus 1. So that's a half x over x squared plus 1. I'll tell you why I'm doing this in a second. Plus c over x squared plus 1. Plus a half over x squared plus 1. Now the reason why I'm going to cut this into 2, and we're going to do it every time, is that we have a formula for integrating a constant over x squared plus 1. It's the tangent inverse of x. This we'll always be able to do with u substitution. If you let u equal the denominator of this fraction, x squared plus 1, its derivative is 2x. And when you end up dividing by the derivative of u, it will cancel the x out in the top, and u substitution will work on this middle fraction. So what I like to do off to the side is go ahead and get the integral of this, and then we'll just paste that in here. So I'm going to go over this u substitution stuff with you. Be a good review for you on u substitution. So for the integral of 1/2 x over x squared plus 1 dx, we let u equal x squared plus 1. Dx is du over 2x. So we have the integral of 1/2 x over u times du over 2x. X is canceled. A half divided by 2 is a fourth. That's a constant multiple. You end up with a quarter du over integral du over u. That's 1/4 log absolute value of u plus c. That's 1/4 natural log x squared plus 1. So I'm going to take this and paste that into my answer. And we can get the original integral done now. So here, negative a half times the integral of 1 over x plus 1. That's minus a half log absolute value x plus 1. This, I'm going to paste in the answer that we just did off to the side. That was 1/4 natural log x squared plus 1. And this one is 1/2 tangent inverse of x. That's a formula that you have memorized. And the problem is done.